All right, today we're going to pull back the curtain on one of the most critical, yet kind of invisible parts of the modern internet, the rate limiter. It's the silent guardian that keeps our favorite apps and services from, completely falling apart under pressure. And we're going to dive into how you design one from the ground up. I'm willing to bet every single one of us has hit this wall. You're trying to refresh a page, hit an API, whatever, and bam, you're locked out. Too many requests. It's frustrating, right? But what if I told you that this error is actually a good thing? Yeah, because that error 429, it's not a bug, it's a feature. Think of this message as a shield. It's protecting services from getting totally overwhelmed, whether that's from a malicious attack or just a user hitting refresh a few too many times. It's the system's way of politely saying, hey, maybe let's just slow down a little bit. So here's the game plan for this explainer. First, we'll hit the why. Then we'll figure out where this thing actually lives in a system. After that, we get to the fun stuff, the brains of the operation, the core algorithms. Then we'll see how to scale it for the real world and wrap up with some key design details you can't forget. Sound good? Let's go. First up, why do we even need to bother limiting requests in the first place? Well, you can think of rate limiters as the essential guardians standing at the front door of any API or online service, and their job is absolutely crucial. It really all boils down to three main benefits. First off, they're your front line of defense against denial of service, or DOS attacks, filtering out those crazy floods of traffic. Second, they can save you a ton of money, especially if your service relies on third-party APIs that charge you per call. And finally, and maybe most obviously, they keep your own servers from getting overloaded, which keeps your service snappy and reliable for everyone else. And this isn't just some abstract idea, right? This is how the web actually works. Twitter limits how many tweets you can fire off. Google Docs caps how often you can read from a document. The biggest players in the world rely on rate limiting to stay online. It's pretty much a non-negotiable for building anything at scale. Okay, so we're sold. We need one. The next big question is, where does it go? Where in our system's architecture does this limiter actually live? On the client? The server? Somewhere in between? Well, we can pretty much immediately rule out putting it on the client side. A rate limit on a user's phone or a browser is just not reliable. A clever user can easily get around it, so it offers basically zero real protection. For the limiter to actually have any authority, it has to live on the server side, where we're in control. And even on the server side, there's the best practice. You want to stick this thing right at the edge of your system. It's often handled by something called a middleware, or even better, an API gateway. That way, it's like a bouncer at the front door. It can reject bad traffic before it even gets a chance to bother your main application. All right, now we get to my favorite part, the algorithms. How does a rate limiter actually decide whether to let a request in or block it? This is the brain of the whole operation, and it's pretty fascinating stuff. So one of the most popular and honestly elegant solutions is the token bucket algorithm. You'll see this used by giants like Amazon and Stripe. The analogy is just perfect. Imagine you have a bucket. This bucket can only hold so many tokens. And every so often, say every second, a new token gets dropped in. To make an API request, you have to spend one of those tokens. The logic is so simple, but so powerful. Tokens get added at a steady pace. Every request uses one up, and if the bucket's empty, sorry, you're denied. But here's the cool part. What makes it so effective is that it naturally handles short bursts of traffic. If you haven't made any requests for a while, your bucket fills up, which means you can then spend all those saved up tokens at once. Now, a simpler way to do it is the fixed window counter. Here, you just chop time into, say, 1-minute chunks. You have a counter for that minute. Every request makes the counter go up. If it hits the limit, no more requests are allowed until the next minute starts, and the counter just resets to 0. Simple, right? But it has a huge flaw, and this slide shows that flaw perfectly. It's called the edge burst problem. Let's say your limit is 5 requests per minute. A user could be sneaky and send 5 requests in the last few seconds of a window, and then, the second the clock ticks over, send another 5 requests in the first few seconds of the new window. And just like that, in the 60-second span that crosses that window boundary, they've sent 10 requests. That's double your rate limit. The algorithm was totally bypassed just because of that hard reset at the window's edge. Not good. The fix for this is the sliding window counter algorithm. It's this really clever hybrid approach that smooths out those edge bursts. Instead of just resetting the counter to 0, it also looks at a weighted percentage of the requests from the previous window. This gives you a much more accurate rolling rate limit. So here's the quick breakdown. Token bucket is awesome for allowing bursts. The fixed window, it's simple, but it's got that big problem. And the sliding window is a much more robust fix for that burst issue. As always, it's a trade-off, right? You're balancing simplicity, accuracy, and performance, and the right choice really depends on what you're trying to protect. Okay, now all these algorithms work just fine if you're running on a single computer. But in today's world, we have distributed systems with dozens, hundreds, maybe thousands of servers. And that's where things get complicated. Exactly. I mean, if each server has its own separate counter, what's to stop a user from just hitting server A until they're blocked, then hitting server B, then server C? The overall rate limit would be totally useless. We need a single source of truth for our counter. But even if we have a shared counter, we run into another classic problem, the race condition. Just imagine 2 requests come in at the exact same millisecond. They both read the counter and see the value is 3. They both add 1, making it 4, and write that back. We just lost a count. The real value should be 5, but our system thinks it's 4. The industry standard solution here is to use a super fast centralized data store like Redis. The magic of Redis is that it provides what are called atomic operations. That means an operation like increase for increment is guaranteed to happen as a single indivisible step. The read, the increment, and the write all happen at once, which completely prevents those race conditions. All our servers talk to one Redis instance, and we get a synchronized correct count across the whole system. All right, we're in the home stretch. We've got the logic, we've got the architecture. Now let's talk about the practical details, the little things that make a rate limiter not just effective, but actually user-friendly. A well-behaved rate limiter has to communicate. It's just good manners. When you make a request, the service should send back a few special HTTP headers. X rate limit limit tells you the total number of requests you're allowed. X rate limit remaining tells you how many you have left. And if you do get blocked, X rate limit retry after tells you exactly how many seconds to wait. It helps developers play by the rules. And that brings us to our final thought. We've spent this whole time talking about how rate limiters are built to control the flow of traffic, but it makes you wonder, in these huge complex systems, what controls the controllers? How do we set these rules, monitor them, and change them on the fly? Now that is a design challenge for another day.